Do you feel like a coffee break? So do I. What about we talk about the Stream API? Once again, the Stream API is going to get some attention in the JDK 24 with the junction of another element called the gatherers. We already talked about gatherers in a previous JEP Café. It's not a simple API, but its goal is to solve a problem that can be stated in very simple terms. So let us talk about it and revisit the Stream API to understand exactly how it is working and what you can do with gatherers that you could not do before they were introduced. You will hear about intermediate and terminal operations, short-circuiting, stream interruptions, bufferization, parallel streams, and non-denotable types. To understand gatherers well, you need to understand how the Stream API is working. So let me take you quickly through the basic principles and also visit some of the dark corners of the Stream API, just to make sure that we are on the same page. Even if you've been writing streams for years, there may be some details here and there that will still surprise you. As you know, a stream does not hold any data. A stream object is basically an empty object. Well, most of the time. You can connect it to a source of data and it will get its data from that source. This is true most of the time because there are streams that can buffer some data, and you will see that in a minute. Most of the time, this source is a collection or an array, but it doesn't have to be. You can stream many things: the lines of a text file, the letters of a string of characters, the elements of a string of characters split by a regular expression, or the elements of a directory tree. Even a random numbers generator can stream the elements it generates directly. And even the foreign function and memory API added to the JDK 22 offers you to stream the elements of a memory segment defined by a memory layout. You can get a memory segment that maps a file in memory, define a layout on it, and then stream this mapped file with a single line of code. So there is in fact no limit to what you can do. How all this has been made possible? Well, beneath the Stream API, there is another API called the Splitterator API. If you want to learn more on this API, you can check the Splitterator interface and see how it has been implemented in the ArrayList class, for instance, or in the HashSet class, or even in a pattern class, and see the differences. Note that in the case of pattern, the Splitterator is built on an iterator that lazily splits the string of characters. So it can be much more efficient to use this pattern rather than splitting your string of characters, building the array of elements, and streaming this array. So in case you want to connect the Stream API to your own source of data, you can do it using the Splitterator API. But the most frequent source of data for a stream is in fact another stream. Calling a method on a stream defines this stream as the source of the data consumed by this method call. Once you have created a stream, you can call methods on it. And then comes the first trap. You can call a method on the stream you created, but just one. If you try to call another one on the same stream object, whether it is intermediate or terminal, then you will get this nasty illegal state exception: stream has already been operated upon or closed. So don't do it. That's the reason why most of the time you will see stream processing written in that way, with chained methods and no intermediate variable. Because there is no point in creating these intermediate variables. You can only call a single method on them. There is nothing else you can do. So exposing such a variable would probably put your code at risk. That being said, there are many methods that you can call on a stream object. We are not going to go through all of them, but I still would like to talk about some characteristics they share or do not share. First, there are methods that return a stream and other methods that do not. These methods always return a new stream object, and there is no method that returns this, which would be the same stream you called this method on. There are sometimes classes that return this, so they can chain method calls on the same object, but that's never the case for streams. These methods that return a stream are called intermediate operations, and we'll see why they are called like that in a minute. Then there are the other methods that return something else. This something else could be a value, like count, that returns a long, or an object, like toList, that returns, well, a list, or void, like forEach, that returns nothing, or max, that returns this funny object, optional. I say it's funny because returning an optional is a way to always return something, but since this optional can be empty, it's also a way to return nothing sometimes. But fortunately, there are also times when it's not empty, so returning an optional is actually a way to return either something or nothing. These methods that return something else than a stream, including void, are called terminal operations. And there comes the second trap of the Stream API. A stream starts processing data, that is, pulling data from its source, when you call a terminal operation on it. If you examine this stream processing, for instance, which is just a mapping and a call to toList, you can see that the toList method call is the terminal operation. Calling this method triggers the computation. The toList call starts the consuming of objects coming from the stream returned by the map method call. Then this stream starts the consuming of objects coming from the stream it is called on, which tends to be directly connected to this list of strings. If you never call a terminal operation on the stream, then this stream doesn't do anything. It does not consume any data. It does not process anything. This object is useless, and even if its operations are doing some side effects, they will never be called. If you see such a thing in your application, well, it's definitely a code smell, and most probably a bug. I just talked about side effects. As a rule of thumb, never do any side effect in the lambda you pass to your stream methods. It's always a mistake to do that, unless you are debugging your code, of course. There are cases where these lambdas are not called by the Stream API, and I'll show you some examples of that in a minute. So that's the first way of qualifying methods of the Stream interface. Some are intermediate operations and others are terminal operations. You can create more categories among the intermediate methods. For instance, there is the one-to-one category. These methods consume an element and produce another element, or no element in a stream they return. That's the case for map and filter. These methods are among the simplest of the API. On the other hand, you have one-to-n methods with flatMap and mapMulti. Flat mapping is a classical operation in functional programming that can flatten a one-to-n relationship between objects. Suppose that you have a stream of countries, and each country has a list of cities. That's your one-to-n relation. Well, flat mapping consists in mapping a stream of countries to a stream of cities of these countries. Odds are that each country will contribute at least one city in a final stream, so you will end up with more cities than you had countries, thus the one-to-n relationship. But you could also imagine a country without any city that would contribute 0 city. So a flat mapping could as well produce no element. There are cases where you can use flatMap when you need to validate the elements of the stream you process. Most of the time, validation can be done with the filtering, but it can also be done with a flatMap. You can do it, but it does not mean that you should do it. As you can see on this example, the code is not very nice and pretty absurd actually. But there are cases where filtering is inefficient. Suppose that you have a list of integers written in a text file, and you need to convert them to real integers. And you know that you have some lines with comments that start with a sharp character. You can filter these lines out with a filter operation and then use a mapping with integer.parseInt to get your integers. But sometimes you may come across lines that are buggy, and there is no way to recover from them. If you want to solve this problem with a filter call, then you will have to write this kind of code. You try the conversion, if it throws an exception, then you return false, which is not great to say the least, because you will have to repeat this conversion again in your mapping operations. So to convert a line to an int, you actually evaluate integer.parseInt twice, which is really inefficient. This is the kind of situation where using flatMap to do some validation may come handy. If you use flatMap, you can return an empty stream if the conversion is not possible. Then, when the flatMap opens the stream you return, an empty stream will not contribute any value to the final stream. This works great, at least you're not doing the parsing twice anymore. But it is still quite inefficient, because you need to create a stream object for every line just to open it immediately. That's an overhead, and you can avoid it. This is exactly why this mapMulti method has been added to the Stream API in a JDK 16. In the end, mapMulti does exactly that, but without having to create this intermediate stream object. The mapMulti method takes a lambda with two parameters. The first one is the object of the stream you need to process, and the second one models the stream this method returns. Here I called it downstream, and this object is actually a consumer, so to pass an object to the downstream, you need to call downstream.accept and pass this object as an argument. But you don't have to, and if you don't, your mapMulti will not pass any object to the downstream, which is okay. In this example, you could accept either once, if the parsing is successful, or not at all. But you could also call it multiple times, so you could actually flatMap the previous relation between countries and cities using mapMulti with the following code, which would be more efficient than flatMap because you save on the creation of all the intermediate streams. There is one point you need to be aware of with mapMulti, which is the following. If you write this code like this, you will see that the exact type returned by mapMulti is actually a list of objects. It comes from the fact that you did not specify the exact type of the downstream object, which is consumer object by default. You can specify the type of object you pass to the downstream when you call this method. This type actually specifies the exact type of the stream returned by mapMulti. So here this type is city, and if you write it in that way, you will get a list of city as expected. Let us take a look at the exact declaration of this mapMulti method. It takes a big consumer that is defined on two types. First, the elements of the stream, and second, the downstream, which is a consumer of R. R being the type of the stream returned by this mapMulti call, which is a little hairy. Some of the intermediate methods in the Stream API can terminate a stream. It means that no more element will be consumed, even if there are more that could come from your source of data. One consequence is really nice. It means that you can connect a stream to an unbound source of elements that can produce an unbound number of elements. And if you call such a method, you make sure that your stream will produce a result. There are two of these methods: limit, that takes the number of elements you need to consume, and takeWhile, that was added in the JDK 9 and does the same but with the predicate. As long as this predicate is true, your stream keeps pulling data from the source, and when it becomes false, it closes the door and the stream terminates. Even if there is some data after that, for which the predicate might become true again, this stream is done. The second category is really important because it shows that an intermediate operation can decide to stop the consumption of source elements. We'll see that it's an important point in the design of the Gatherers API. Bear with me, we have two more categories of stream operations to go through before talking about gatherers, plus one. So the next is made of methods that can delay the start of your computation. There are two methods that can do that: skip, that takes along as a parameter, which is simply the number of elements you want to skip before starting your processing, and drop while, that was added in the JDK 9, that takes a predicate, and the processing of elements starts when the predicate becomes true. Note that past this point, this predicate is not evaluated anymore, so even if this predicate becomes false again, it has no impact. There is something that is worth noting in the last two categories: the one with skip and drop while, and the one with limit and take while. To properly work, these methods need to store an internal mutable state. The skip and limit methods must have an internal counter, and the drop while and take while methods needs to know if they should continue evaluating their predicate. So an intermediate method can interrupt a stream or delay the processing and can have an internal mutable state. Let us keep that in mind for the Gather API. The last category I would like to mention is made of methods that have to bufferize all the elements of your stream before being able to produce any in a stream they return. The fact is, you cannot use these methods on a stream that can produce an unbound number of elements, because if you do so, you will never see the end of your stream and you will be good to restart your application. There are two methods like that. The first one is sorted. This method puts all the elements of your stream in an array, then sorts this array when all the elements of your stream are in it, and then send these elements one by one to the stream it returns. So never try to sort an unbound stream, because sorted will never produce anything. And it will try to store an unbound number of elements in an array, so at some point it will run out of memory space and throw an exception, usually an out of memory error. The second method that has this kind of behavior is the distinct method. This method works in a slightly different way. It adds the elements of your stream in a hash set. That may be a linked hash set, sometimes for ordered streams. And when adding an element to the set returns true, which means that this element was not in the set previously, it passes it to the stream it returns. So instead of producing all its elements at once, it will produce them once at a time when it sees a new one. So on an unbound stream, distinct can produce an element from time to time, but will never return neither. So don't do that. So that's a third behavior different from the others. These methods can have large internal buffers and decide to produce elements when they see fit. It could be all at the end or one at a time. I promised you a last bonus category, so here it is. It is the category of the methods that you should not use. And there is one method in it, plus another one. The method you should not use is the peek method. This method was added mostly for debugging purposes, and you should only use it for that. Especially, you should absolutely avoid doing some side effects in this method, like adding the element it processes to an external list. The Stream API uses many optimizations internally, and some of them consist in not calling all the lambdas you add in your pipeline, because sometimes they are not needed to produce your final result. If you're not convinced, you can just try to run the following example and see by yourself that the list is actually empty. Where does it come from? Well, the reason is a little subtle. It turns out that the stream on which you call count is sized, meaning that the Stream API has access to the number of elements this stream will produce before it starts producing them. Well, if you know this number, you can just return it, right? And not consume the elements at all. You will save on the execution of all the lambdas in a pipeline, which is much more efficient. But in the meantime, the side effect in the pick method is never called, and you end up with an empty list. If you had a filter operation, for instance, then the stream returns by the call to filter, remember it's a new stream object, is not sized anymore. So the side effect is called. So don't do any side effect in your stream operation. You will create places for bugs to hide, and that is never a good idea. I just told you about a stream that is ordered or sized, and you may be thinking, okay, ordered stream is a stream that has an order, like a stream created on a list. A stream created on a set, on the other hand, is probably not ordered, since the elements of a set are in no particular order, which is the case. Actually, every stream has a set of characteristics that can be used by the different implementations of the stream operations. These characteristics are defined in the splitterator interface. One of the characteristics is distinct, meaning that this stream does not contain objects that are equal. For instance, when you call distinct on a stream, what you get is a stream that has this characteristic, distinct, meaning that if you call distinct again, well, there is no need to do anything because this stream is already distinct. Same if you create a stream on a hash set. Calling distinct on such a stream doesn't need to do anything because your stream already has this characteristic. The last method you call on a stream is the terminal operation on the stream, or at least it should be. If it is not, then your stream pattern has a problem. And again, there are several categories of them. Let me put forEach and forEach ordered in the first category. forEach is somehow like pick. Using it when you want to debug or want to check what your stream is doing is fine, but in most of the other cases, you are probably using it wrong. I would say not all of them, because there are cases where a forEach can simplify the way you write a for loop. But it is still a side effect, and you need to be cautious with that. Note, by the way, that you also have a forEach method directly on collection, and sometimes creating a stream to call forEach is just useless. The forEach method is some kind of a category of its own. It does not really represent what the terminal operations are. In the second category, you find methods that are classical reductions in a general sense. The stream API gives you a min, a max, or a count. If what you have is a specialized stream, namely int stream, long stream, or double stream, then you will also have an average method and a sum method. And these methods do what you think they're doing. The only unexpected thing is that min, max, and average all return optionals due to the fact that these reductions do not have an identity element. Since the reduction of an empty stream must return the identity element of the reduction operation, this is the way to tell the caller that an empty stream was reduced. This is actually needed to guarantee that your reductions are correct. And if you're not happy with these basic operations, you can still implement your own with the reduce method. This method comes in two flavors. A first one that takes the identity element, and it better be because this element is used as the first element of your reduction, and the second one that does not. And because it doesn't have an identity element, this second reduce method returns an optional. And there is a third one that takes an accumulator and a combine. The third category is quite special because to produce a result, these methods do not always need to consume all the elements of your stream. That's the case for find first or find any. As soon as you find an element, you can return it and that's it. All the rest is not needed anymore. That's also the case for all match, any match, and non-match. They all take a predicate as a parameter. For instance, if all match finds one element for which the predicate is false, then it can immediately return false. Because of that, these methods are called short-circuiting and constitute yet another category of terminal operations. Note that find first put a constraint on the element it returns and can only work properly on a stream that has an order. Fortunately, the ordered characteristic is there to help the API. Note that find first and find any return an optional to properly handle empty streams. Then the fourth and last category is also about reducing your stream, but this time in a mutable container. And that's the job of the collect method that receives a collector. And then you need to understand the collector API, and let me tell you this, if you like the collector API, you will love the gatherer API. I would like to spend some time on this collector API because the gatherer API is built on the same principles and also suffers from the same drawbacks. The idea of the collector API is to offer you the possibility to create your own terminal operation. And it works quite well. You can collect the element produced by your stream in almost any way you want with a collector. Odds are that if you're using collectors, you are calling one of the methods of the collectors factory class. There are a little more than 50 methods in this class, so it's a little hard to understand everything, but fortunately some of them are very simple. For instance, collectors.toList gives a collector that puts the element of your stream in a list, and collectors.toSet in a set, which is pretty simple. Collectors.joining works on stream of strings of characters and join all these strings. It also has overloads to pass a separator, a prefix, and a suffix. Collectors.groupingBy is really nice. It looks like the group by you have in SQL. It takes a function as a parameter that is applied to the elements of your stream. This function produces a key for each of your elements that is used to store each element in a map. But of course, this function may produce the same key for two different elements. These elements are added to a list bound to this key, so this collector creates a map of key and lists of elements of your stream. If there is no collision for a given key, then the list contains only one element. And the nice thing is that you can compose collectors. For instance, if you don't want the grouping by collector to create lists but sets, then you can pass the collectors.toSet as an argument to the grouping by. Or if you want to count the number of elements bound to each key, there is a collector for that you can pass as a downstream collector to the grouping by method. It's the collectors.counting collector. You can create your own collector by using the factory method of defined on the collector interface. And the first thing you need to set up are the types that this method needs. It's not that hard, there are two of them. The first one is the type of the stream this collector can collect, and the second one is the type that this collector returns. Internally, a collector works with 3 elements plus 1. A collector collects elements in a mutable container. So the first element is the one that can create this mutable container. It's a supplier of container. For the collectors.toList, it's simply ArrayList column new, and it's the same for the collectors.toSet. This supplier is just hashset column new. By the way, if you want to use your own collection, you even have a collectors.toCollection factory method that takes such a supplier. The second element a collector needs is the element that can add an element of your stream to this container. It is modeled by a lambda, of course, that takes your container, the one that you're filling with the elements of the stream, and the next element of the stream you need to add. And this lambda does not return anything. The second element is called the accumulator, and its type is a big consumer. In the case of collectors.toList, or toSet, by the way, this accumulator is simply ArrayList column add or hashset column add. Pretty simple. And if you think about it, that's all you need. One method to create the mutable container, and another one to add an element to it, and that's it. One supplier, one accumulator, and you're done. But there are two things you need to think about. The first one is that the stream can be parallel, and the collector API needs to support that. We'll talk more about parallel streams in a minute, but for now, all you need to know is that your source of data is divided in small chunks, and each chunk is processed in its own thread independently. So in that case, a collector needs to be able to merge two containers filled in different threads by the parallel algorithm. This third lambda is called the combiner. It takes two containers and it should merge them together and returns one. So its type is a binary operator that can operate on your container. In the case of our good old friend collectors.toList, it's basically add all, and the same for collectors.toSet. It's actually slightly more complicated than that because add all does not return the collection, so you cannot write it as a method reference. With all these three elements, you should be able to create your own grouping by. It's not as easy as toList, but not too hard neither. There is still one element that is missing though, because we've been talking about mutable containers since the beginning, and I sneaked in the collectors.joining collector as an example, which is collecting in a string. And at least the last time I checked, strings are not mutable containers, are they? So the question is, the pattern I just showed you with the supplier, the accumulator, and the combiner, how could it produce strings of characters? Well, the answer is it can't. But what you can produce are string builders, because these are mutable containers. And on this string builder, all you need is to call toString to get the string you need. This last operation, this finishing touch, to create exactly what you want, is supported by the collector API, and it is called the finisher, precisely. Now, be careful because to pass this finisher, you also need to pass its type. So the auth method now needs 3 types instead of 2. The third type is the return type of your finisher. You could be thinking that it's only useful in the case of the collectors.joining collector. But in fact, you can use it every time you want to produce a non-modifiable container, like an unmodifiable list or map. So it's actually very handy. All this is great. You can do many things with collectors, including mapping, filtering, flat mapping, and composing that with the accumulation in a mutable container. But the way it has been designed makes it so that you do not have access to the stream you are working on. The stream instance itself, you don't see it from the lambdas of your collector, which is a drawback because sometimes it could be interesting to get the characteristics of the stream if you could know in advance that no element from the stream can be null because the stream is non-null, or all different because the stream is distinct, or that the stream will send you a given number of objects because it is sized. You would probably write your collectors in a different way. But you don't. A collector is an object that does not know that it's being used to collect objects produced by streams. And by the way, you can perfectly use your collector outside of the stream API if this is what you want. You can actually run this example with any collector you can write, thanks to the use of the var keyword, no stream here, just plain collections and their forEach method. What about going parallel with your streams? Being able to compute everything in parallel is one of the amazing features of the Stream API. It leverages the multi-core nature of your CPU by distributing your computations among all of them, which is great. The only question you need to ask yourself is the following: is it worth it? What performance gain can you expect? So let us spend a few minutes understanding how parallelization works in a Stream API. When you decide to go parallel with your stream, the internal algorithm of the Stream API splits your data in 2 pieces of data and runs your stream on these 2 pieces. Then each of these pieces is split again, and again, and again, until the algorithm decides that the number of elements that each stream has to process is small enough and that it can process them as a normal stream. Every small piece is computed as a small normal stream by a different thread taken from a special pool called the common fork join pool. there is only one such pool in your JVM, so if you launch several parallel streams computations in your application at the same time, in different threads, there will be a competition on the use of these common fork join pool threads. It may not be a great idea to do that. It's really up to you to evaluate the real gain you have in your production environment. At the end of the day, you will have a number of partial results that the parallel stream implementation needs to merge together again, and again until you have your final result. What is this merge function and how does it work? Well, it depends on your final operation. If it is a classical reduce operation with a binary operator, then it is this binary operator that is used. And if you want this to work, you need an associative binary operator. If it is a collector, well, every collector has a special component called the combiner, and this combiner is precisely used for that. If it is a terminal operation like average, then under the hood there is a combiner that is doing the merging. And you can also have merging with intermediate operations. For sorted, for instance, this merging is done with a special algorithm called merge sort that can efficiently merge two sorted arrays. So there are three key points in parallel streams that you need to check in order to know if it is a good idea to go parallel or not. And the fourth one, that does not depend on your stream. The first one is you need a data source that you can split in two parts again and again. And more than that, when you split it, you need to be sure that you have the same number of elements in both parts. That's the case for array list. You know how many elements you have in your array, and you know where to split it, to split your data in two equivalent pieces. But that's not the case for hash set, for instance. Hash set also wraps an array, and you know how many elements you have in that array, but they are randomly distributed in this array. You don't know where they are exactly. When you split this array in two, if you're unlucky and have plenty of collisions in your hash set, you may end up with all the elements in the same bucket and in the same half of this array. So if you split this array in two, you may end up with no elements in the first half and all the elements in the second half. Parallelization cannot work well on such a source. If your source is the splitting of a string using a regular expression or the lines of a text file, the situation is even worse because you do not know in advance how many elements you are going to process, and there is no way you can split it into halves. How is the splitting working in these cases? Well, it actually slices your source of data and sends each slice one by one to your stream computation. By the way, there are two characteristics for that to know if your source can be split. The first one is sized. A stream that is sized knows how many elements it will produce in advance. That's the case for array list. And the second one is subsized. A stream is subsized if, when you split its source, you still know how many elements you will get in each half. And again, that's the case on array list. A stream build on an array list is both sized and subsized. A stream build on a hash set is sized, but not subsized. And a stream built on the lines of a text file is neither sized nor subsized. Parallel streams work better on sources that are both sized and subsized. The second one is about concurrency and side effects, precisely. You saw that the lambdas you pass to the different methods of your stream are going to be executed in different threads. If you are doing side effects in them, like adding elements to an external array list, what you're doing is actually adding elements from different threads to a single array list. As you know, ArrayList is not a thread-safe structure, so you have a race condition here. Once again, don't do any side effects in your streams. The concurrent nature of parallel streams may have an impact on the implementations of the intermediate methods that we just saw. The distinct method, for instance, manages an internal mutable state. Well, with parallel streams, it becomes a shared mutable state that needs to be protected against race conditions and visibility issues. Which is the case, don't worry. The same goes for limit or drop while, where the internal state managed by these methods is now shared among different threads. And by the way, limit of 10 tells you that it takes the first 10 elements of your stream. So the counter needs to be unique and shared among all the threads to make sure that this is the case. For sorted, the situation is even more complex. Each thread can sort its portion of your stream using quicksort, and then all the small sorted portions are merged together using yet another algorithm called merge sort. Merge sort is fast, no problem, but it is still an overhead. And the third one is about the nature of the reduction operation. Parallel streams are computing partial results and are merging them using the reduction you defined. So it means that your reduction needs to be associative. We already saw that. Because the reduction of the partial reductions needs to be the same as the global reduction. And that's precisely the definition of associativity. What happens when your reduction operation is not associative? Well, precisely nothing. No compiler error, no exception at runtime, you will get a result, no problem. Is this result going to be the same one as the one you would get with a non-parallel stream? Well, it could be, if you're lucky. When it comes to associativity, you're really on your own. And then there is a fourth one that does not depend on your stream itself. Parallel streams try to use all the cores of your CPU. Having several threads in your application running parallel streams at the same time will probably do you no good because your CPU is already busy. Putting more load on it will not speed up your computations. Suppose you are in a REST server application, for instance, optimized to serve as many clients as possible, or in a complex reactive application that uses your cores to optimize the throughput of your application, running parallel streams is an overhead that will hit the global performance of your application. This is probably a case where you do not want to go parallel. Now, we can start talking about gatherers. That was a long introduction, but trust me, we are going to use every single piece of what we covered to understand how gatherers are working and why they have been designed in that way. The Gatherer API is about creating gatherer objects. From a technical point of view, there are three elements to this API. First, an interface, gatherer, that models a gatherer. Second, a method on the stream interface called gather that takes a gatherer as a parameter. And third, a factory class, gatherers, with some pre-made implementations of this interface. You can think of a gatherer as an object that models an intermediate stream operation, just as a collector models a terminal operation. Gatherers and collectors are kind of the same. They give you the possibility to create operations for the Stream API that exactly fit your needs. Collectors are for terminal operations, and gatherers are for intermediate operation. But as you saw, an intermediate operation is more complex than a terminal operation. It is an element of a chain of operations in a stream. It takes its elements from an upstream and produces elements to a downstream. The collector sends its elements to a mutable container that it owns itself, so it's much simpler. Let us start from the beginning and write some gatherers to see how this object is working. I think that a good place to start is to take the simple intermediate operations, the ones that are one-to-one, stateless, non-terminating, non-nothing. And we have two of them, map and filter. The map method is probably even simpler because it passes what it gets with just a transformation. It does not decide to pass the elements it gets or not, as filter does. So let us implement a basic mapper with a gatherer. Let us take the following example. You have a simple stream of strings. You map it to uppercase, put the result in a list, and print the list. Pretty simple. Let us write a gatherer to do the same. There is a nifty factory method on the gatherer interface called off that can build gatherers for you from the elements they need, just like the collector.off method we used a few minutes ago. This method defines type parameters. The first one is the type of the elements of the stream this gatherer consumes, and the second one is the type of objects this gatherer can produce. Here we model a two uppercase mapper, so both types are string. There are several overloads of the off method. We are using the simplest one here that takes only one parameter. This parameter is of type integrator, and its role is to integrate a new element to the stream produced by this gatherer. Integrator is a functional interface, and the lambda you need to implement takes three parameters. We are not using the first one for now, so let us use this underscore parameter that is just telling that. The second one is the element of the stream you need to process, and the third one model the downstream this gatherer is pushing elements to. And to push an element, all you need to do is to call downstream.push and pass the element as an argument. Simple enough. Now, you need to be careful, because this lambda must return a boolean. But it turns out that the push method also returns a boolean, so the compiler is happy in that case. We'll see what is this boolean exactly in a minute. And by the way, if you have a stream of countries, and each country has a list of cities, then you can also flatMap this stream of countries to a stream of cities with this pattern. You can call this downstream.push as many times as you need in your implementation. So this is the first pattern given to you by the gatherer API. Calling gatherer.off or gatherer.off sequential and passing an integrator as an argument creates a gatherer. You can use it in parallel or not. More on that in a minute. Now, you saw that calling downstream.push returns a boolean that we didn't take into account, and so far all the integrators we wrote returned true, because why not? So let us look into this and talk about interrupting gatherers. You remember that in a stream API you had several intermediate operations that can interrupt your stream. These are limit, take while, skip, and drop while. Internally, these intermediate operations do two things. First, they decide to interrupt your stream. And remember, interrupting is not the same as filtering. And second, they need to manage an internal state. Limit and skip have an internal counter that is a mutable state, and that can be shared among different threads in case of a parallel stream. And the same goes for drop while and take while. They need to manage an internal mutable state to know if they are opened or closed. So let me show you how you can implement a gatherer that will just limit the number of elements to a given number. For that, you need to store a mutable state that can count the number of elements you already processed from the stream. So let me create a mutable container, the simplest you can imagine, In fact, a simple class will do. Then you need to tell the API how to build an instance of this mutable container in the form of a supplier. And by the way, let me call gatherer of sequential. Gatherer of sequential means that this gatherer does not support parallel streams, which does not mean that you cannot call it within a parallel stream. We are going to talk more about that in a minute. So for now, this mutable container is just this one. It's not thread safe, and that's okay. We are using it in a sequential gatherer. Don't worry, we'll see how to support parallel streams in a minute. Now you need to pass a lambda that implements the integrator interface. And you remember that for the mapping, the filtering, and the flat mapping, we ignored the first argument of this lambda. Well, this argument is actually the state object precisely, and in that case, it's your instance of counter. You didn't need it in the previous examples, but now you do, so you can't ignore it anymore. So now you can implement the limit behavior. Pretty simple. If count is lesser than limit, you can increment it and push the next element. And you return true in the end, at least for now. Now you have a factory method that creates a gatherer that will stop passing elements to the downstream after a certain limit. Great. Are you done with it? Well, not quite. I would like to dig a little deeper. Let us see more precisely how this limit method is working. Let me run this code where the mapper prints a message on the console. And as you can see, the mapping is applied to the first 3 elements of the stream. Why? Because the call to limit interrupted the stream after 3 elements, so no unnecessary mapping was computed. The stream API is smart. Let me try the same with our limit gatherer. And as you can see, it does not work so well. The stream is actually not interrupted. Everything continues, and some unnecessary mappings are computed, which is a waste of resources. To prevent that, you need to correctly manage this boolean returned by the integrator. So far, we always returned true. If you return false, then what you are telling the stream API is that you are not going to push any more elements to this downstream. And the stream API will react accordingly by interrupting the stream. And by the way, because this downstream may itself interrupt the stream, before doing anything, you should check for that in your integrator implementation. There is a isRejecting method on the downstream interface that you should check before doing anything. And if it returns true, then you should not push any element to it. So let us fix this code. First, you need to check if the downstream accepts more value. You need to call downstream isRejecting for that. And if it does not, then you don't need to do anything, and you can return false to notify your upstream that you're not accepting any more element neither. Second, you need to check if your counter is still within the limit. If this is the case, then you can push the element to the downstream. And third, you need to decide if you will be accepting more elements or not. If yes, you need to return true, and false if not. Here, all you need to do is to check how many elements you already pushed, and if you reached the limit, then you need to return false. There is an element I need to mention here. Instead of passing a simple integrator to this method, you can also pass a greedy integrator, modeled by the greedy.integrator interface. What does this greedy integrator do? It never interrupts a stream on its own. It should only propagate the result of downstream.push. If you pass a greedy operator, then the stream API will be able to use some optimizations to process your data faster. You don't need to do that, your gatherers will work anyway if you don't, but this is something you can do. So at this point, we have a working gatherer that is implementing limit. And I know what you must be thinking about. What's the point of having such a complex API just to implement limit? Yes, all this stuff is complex, I agree. So let us create a gatherer that can do something that the stream API cannot do. Suppose that you have a stream of numbers and you want to create a stream of lists of numbers, each list containing 2 consecutive numbers from the stream. So if you have 1, 2, 3, 4 in your stream, you want this gatherer to build a stream with 1, 2, then 2, 3, then 3, 4. Like you are sliding a window on the stream of size 2 and take the elements in that window. This is something you cannot do with a regular intermediate operation, unless you want to play with an external mutable state, something you should definitely not do. So let us build a gatherer to do that. This gatherer is creating a stream of list of t from a stream of t, so this is its type. It needs to have an internal mutable state, so you can take the model of the limit gatherer you just built in the previous example and call the class that modeled this mutable state sliding window, for instance. Then you need to call of sequential because this gatherer will be used sequentially. The first argument is the supplier, so it's just the constructor of your sliding window class, and the second one is the lambda that implements the integrator that takes the state, the element, and the downstream as arguments. First, this lambda needs to handle the case where your downstream is not accepting more elements, and this code is the same as the previous example. Second, you need to add the elements to your list, and if this list has the right size, then you need to push it and remove the first element. And at the end of the day, you can return true because this gatherer is not interrupting the stream. By the way, you could also create a greedy integrator, as I just showed you. All you have to do now is to test this gatherer to see that it is working as expected. Neat. Let us modify this sliding window to a window that is not sliding. What I would like to have now for a stream 1, 2, 3, 4 is 1, 2, then 3, 4. Easy enough, it's almost the same as the previous one, so let me bring the code again. I'm going to call it fixed window because why not? And now, after having pushed the window, instead of removing the first element, what you need to do is to clear it so that it will be filled with the new elements. Super simple modification. Let me run it on the previous example. This gatherer is working as expected. Great. Let me run it on a more complex example. The list is now 1, 2, 3, 4, 5. Yes, that's more complex. And you see something weird is happening. It looks like this 5 did not make it to the final stream. If you take a closer look at the code we wrote, you can see that we are pushing the list of our internal mutable state only if it has the right length, that is 2. So when this code processes the 5, it adds it to the internal list, does not push it because it doesn't have the right size, and since it's the last element of the stream, this list is never pushed. Written in that way, this code is incomplete. You may end up with an internal state that is never consumed just because the stream is done producing elements. Turns out that the gather API gives you an element to manage this situation. You probably remember that the collector API has a finisher to put this final touch to the mutable container it creates and to make it non-modifiable, for instance. Well, the gather API also has a finisher that can put its final touch to the downstream it pushes elements to. This finisher is a lambda that takes 2 parameters, the mutable state of your gatherer, and that's exactly what we need because this is where our data is, and the downstream. It does not take any element because it is called when the upstream is done producing elements, so there is no more element to consume. This finisher can then examine your mutable state and decide what to do with it. It could even do something if this state object is empty, by the way. Here it's not. There is something left in it, so you can decide to push that. Of course, you still need to check if your downstream is accepting new element before doing that, as usual. Note that this finisher does not need to return anything, not true nor false, because nothing will be called after it. So it's really a big consumer. Now, if you run this gatherer on the 1, 2, 3, 4, 5, you will have the following result: no element was forgotten. Note also that if you want to implement a different behavior, well, you can. The finisher is there exactly for that. So far you saw that a gatherer is built on an integrator, that it needs to handle the fact that its downstream can be rejecting or not, and that it can manage an internal mutable state. We haven't talked about parallelization yet, so let us do that now. You remember that to handle parallelization properly, collectors had to provide a combiner. Well, it's the same for gatherers. Gatherers can have a combiner, and they need to have one to fully support parallel streams. When you use a gatherer to process a parallel stream, several instances of your state are going to process chunks of data from your stream in different phases. And at some point, the Stream API will have to merge all your results. So this combiner takes two instances of the internal state your gatherer is managing and merges them together into one. Let us create an example of a gatherer and let us create the combiner it needs to support parallelism. Suppose you need to count the number of elements you see in a stream and you want to produce a stream that tells you how many times each element was seen. So the elements of the downstream are map.entry objects, the keys are the elements of the stream, and the value are the number of times this element is in the stream as a long. The full type of this gatherer is the following. It's a gatherer of T, that is the type of the elements of the stream, something for the internal state, and map entry of T and long. The internal state has to be a map, since we are counting the number of elements of the stream until all the stream has been consumed. And because we are counting these elements, the value of the map are mutable boxes of longs that you can call counter because why not? This gatherer works in the following way. First, it needs to process all the elements of the stream and to count them. So it's working in the same kind of way as the sorted operation from the Stream API. This intermediate method does not produce any element until it saw all the elements of the stream. How will your gatherer push its element to the downstream? Well, that is going to be the work of the finisher. So let us write all this. First, the supplier. Writing the supplier is pretty straightforward. The supplier is just a constructor of the hash map of the right type, pretty simple. Second, the integrator. The integrator is a little less simple. First, it takes three parameters, your map, an element of the stream, and a downstream of map.entry of T and long. The map is your internal mutable state created by the supplier. The element of the stream is just that, an element of the stream, and the type of the downstream depends on what you need to do. First, you need to check if your downstream is still accepting some data. Since this integrator is not going to push any data, getting a false in this test would mean that your downstream does not accept any object. It may sound weird, but it is what it is. And in that case, whatever you do, you will not be able to push it. So don't bother processing anything. You can just stop here. If you can push some data, then it makes sense to fill your map. Filling it is a job for compute if absent. If the object you need to add to the map is not already in it, then compute if absent invokes the lambda you pass as an argument and binds the result produced to the key and returns it. If it is, then compute if absent just returns it. In both cases, all you need to do is to increment the counter. And in the end, you return true to process the next element. So when all the elements of the stream are processed, Your internal mutable state is a map of elements, and counter, where counter wraps the number of times each element was seen in a stream. The last step is to push the results you need to the downstream with the finisher. The type of this finisher may look a little complex. The first parameter is the type of your internal mutable state. Here is just the map you have been working with. And the second parameter is the type of your downstream. And what you write is a big consumer of this state and downstream. The exact type of this downstream is for you to decide. This is actually what your gatherer is producing. Here we decided to push each map.entry of the map with a little mapping for the value because we do not want to expose the counter class. This class is an internal class that we just created to conduct the computation. It is carrying a mutable state. The exact final type we need is map.entry of t and long, with a little generics magic to make it work. First thing, check if the downstream needs more values or not. If not, then there is no need to push anything. Second, you can stream the key value pairs of your map to push them to the downstream. But before that, there are two things you need to do. First, you need to map them, to open the counter and extract the value it wraps. And second, before pushing it, you need to make sure that the downstream is not rejecting these new elements. That's exactly the job of the take-while method. Its result does not depend on the element of the stream it processes, only on what the downstream rejects or not. So now you have the three elements of your gatherer. You can write it in that way and check that it gives you the right result. Now that you have a working gatherer, let me show you how you can modify it so that it can support parallel streams. Note that if you pass this gatherer to a parallel stream, it will not throw any exception. When I say support parallel stream, it is really about using the API to create this gatherer. So to go parallel, you need two things. First, you need to call gatherer of and not gatherer of sequential, quite obviously. And second, you need to provide the combiner. You also have this combiner in the collector API that is used for the same kind of things. The combiner you need for a gatherer looks like the one you need for collectors. The nice thing with the gatherer API is that if what you need is a non-parallel gatherer, then you don't need to provide a combiner. In a collector API, you always need to provide a combiner, even if you have no plan to use this collector in parallel streams. And it's a pity because in that case, this combiner will not be used. So what's the purpose of this combiner? Well, the parallel stream API uses this object when it needs to merge two instances of your state object. In our example, it's the map of t on counter object. The type of this combiner is simply a binary operator of this state object. So it takes two instances of map of t and counter and returns an instance of the same type. It could be one of the two maps that has been updated with the content of the other, or a new one. Here we are going to merge the two maps in map1, so we return map1. There is a method to merge a key value pair with an existing map, which is the merge method precisely. So you can loop over all the key value pairs of map2 and merge them one by one into map1. This merge method takes three parameters. The first two are simply the key and the value that you want to add to map1. It's the key and your counter instance. If the key is not in the map, then this key value pair is simply added to map1. And if it is, then you need to use the third argument. This third argument is only used if the key is already in a map. In that case, what you need to do is merge the existing value, bound to this key, and the new value that you want to add. This is done with a merge lambda that takes the two values and returns a new one. In this case, the merging is pretty easy. All you need to do is to add the two longs wrapped by the two counters. And once you've done that, you can create your parallel gatherer with the gatherer of method that takes the four elements initializer, integrator, combiner, and finisher. And hopefully it will work as expected. What happens when you pass a non-parallel gatherer to a parallel stream? Well, actually, things are not going that bad. The Stream API does not have a combiner for your gatherer, so it cannot create more than one state object for your gatherer to do its computation, because if it did, it would not be able to merge them together. So it is working with a single state instance, but since it is in a parallel world, this state instance can still be moved from one thread to the other of the common fork join pool. And all the other stream operations can be executed in parallel. If you have a mapping or a filtering before the call to your gather method or after these methods, they will be executed in parallel. So a non-parallel gatherer can still be used in a parallel stream. The gatherer itself will not be executed in parallel, but all your other operations will be. So depending on what your stream is doing, it may be interesting performance-wise to do so. Like always, when it comes to performance, measure, don't guess, and measure using your production environment while your application is running. This environment, most of the time, is very different from your development environment. Now is the time to do a little wrap-up of all this. First idea, gatherers are there to model intermediate operation in a Stream API. You can think of gatherers as some kind of collectors for intermediate operation. Second idea, gatherers support the feature that intermediate operations have. They can push any number of elements to the stream they produce, even 0. They can interrupt the stream, and they can be executed in parallel. Third idea, they can carry a mutable state. Fourth idea, you can compose gatherers together. Fifth idea, gatherers are created using factory methods and are built on 4 elements, a mutable state, an integrator, a combiner, and a finisher. All gatherers need an integrator, and depending on what you need to do, you may need or not the other elements. And with this, I'm out of coffee, so that's it for today. Talk to you soon.